Hey everyone. In a previous video I went through some of the theory behind the ideal gas law, and I explained to you what an ideal gas is and what makes it unique. This video is going to focus mainly on just solving some problems with ideal gas law. And we'll start here with just a sort of a broad overview of what the ideal gas law does differently than the regular gas laws, and then we'll get right to the math as quickly as possible. So first things first, we know that the other gas laws, like Boyle's, took two variables at a time. In case of Boyle's, it was P and V, and looked at the relationship between those two as they changed, and the other variables, N and T, were held constant. Charles's law took variations of V and T, but held P and N constant. So we kept playing this game of taking two variables, holding two constant. In the most recent video you probably watched, with the combined gas law, we took three variables, P, V, and T, and varied those while holding only moles constant. So now with the ideal gas law, we're kind of going the whole way. We're taking P, V, T, and N, and we're going to put in all of the relationships now, including Avogadro's relationship. So we have P, V, and then we put in T, like we saw with the combined gas law. But this time we're also going to have an N. And we see here, if we cover up the P and the T, you can see Avogadro's laws there, V over N. And so that actually forms another proportion, P2, V2 over T2, N2. We almost never work the ideal gas law in a proportion like this. That's just not what we do. Usually, what we do with the ideal gas law is just take one set of conditions and we try to find some information about the amount of the gas, normally moles, but we could also use this to find mass, molar mass, or even density. So what is it being held constant here when we do work with the ideal gas law? Well, the thing that's constant is one of our physical constants in science that we call the universal gas constant. We give it a capital R. So that is the universal gas constant. The most common value that you're going to see, well, I guess maybe you'll see, not on this worksheet that we're going to do, but 0.0821 liter atmospheres over moles K. And then if we change the values of, the units of pressure, the value of the number is going to change a little bit. It's the same quantity, just the number is going to change as we change the descriptor here, which is our unit. So we'll get to that. Yeah, let's just get going here. So let's look at number one. What pressure is required to contain 0.023 moles of nitrogen gas in a 4.2 liter container at a temperature of 20 Celsius. So a couple of things here. Number one, what we've been preaching to you before about Celsius, it still applies. We can't do Celsius, so we got to add 273 to this, and our temperature needs to be 293 Kelvin. We're not going to plug in Celsius here either. So what is this equation that I'm going to plug into? Well, it's this one. I'm just going to rearrange it into what we normally call the ideal gas law. I'm just going to multiply both sides by N and T, nRT, and we call that pivnert. So we're going to plug into pivnert here. Our variable is the pressure, so we're going to say P. In this problem, our volume is 4.2 liters. We're given N to be 0.023 moles. I'm going to use the 0.0821 liter atmospheres over moles Kelvin. And the temperature that we just calculated, 293 Kelvin. So that's it. I've subbed into pivnert with all the information that I need, and I'm going to divide both sides by 4.2 liters. And that's going to give me the pressure that I'm looking for. So we'll do that real quick. We'll go ahead and put those numbers in. 0.023 times 0.0821 times 293. And then I'm going to divide that by the 4.2. Alright, so I get the pressure, and I'll round to 2 sig figs here. 0.13. What about the unit? Let's take a look at our algebra here. From this gigantic expression, I can see the kelvins will cancel from my R value. Same thing with the moles, so they'll go away. And then it's a little bit harder to see here, but I have in the numerator a liter on top in the numerator, and then a liter on top in the denominator. So that's a complex fraction, but it does cancel out, and it leaves me with an atmosphere. So my pressure comes out in a correct pressure unit, 0.13 atmospheres. That's a pretty straightforward problem. All right, we're going to go down to number 3. Number 2 here, once again, is very similar to number 1, so you're going to be kind of bored by that one probably. But let's take a look at number 3. How many moles of chlorine gas would occupy a volume of 35.5 liters at a pressure of 100 kilopascals? And that's important because I can't use the same R value now. And a temperature of 100 degrees Celsius. You got to watch out for that. So let's just stop there and let's go ahead and find those moles. So we're going to take PivNert. And I have another suggestion here that we'll implement for the first time on this problem for those of you who don't like algebra as much. Some of you may find it easier to move the variables around in this original equation. So for example here, I want N by itself. It says how many moles, and that's N. So what you can do is just do a little algebra with the variables to rewrite the equation for what you want. So here N will be PV over RT. That may help some of you. For some of you, that may be an unnecessary thing to do. You make that decision. All right, so let's go ahead and plug in though. Our pressure this time is 100 kilopascals. I'm not going to write all the sig figs, but I am going to remember them when I go back and round my answer. And then we're going to get volume, 35.5 liters. The R value here is going to be different because I have the kilopascals. I can't use the atmosphere one. So what I've got to do is actually a pressure conversion, 0.0821 atmospheres, and I've got to convert that to pascals. Actually kilopascals. So that's 101.3 kilopascals per atmosphere. So that's 8.31 liters kilopascals over moles K. A little bit different looking. It's the same amount, just a different number because the unit changed. And then our temperature here, not 100 Celsius. We're going to add 100 plus 273, so 373 Kelvin. We've subbed our numbers in. Everything's already in its proper place, so we can just simplify. So 100 times 35.5 divided by 8.31, and then one more time divided by 373. So we get 1.15 moles of chlorine gas. Now this problem did give us a little part B here. I quit reading earlier. It says after determining the number of moles, calculate the number of grams of chlorine. And this is something we frequently have to do with the ideal gas law. It can really only give you moles unless we rearrange it, and we don't really want to do that. So we're going to remember something pretty basic. We're just going to do a regular old mole to mass conversion. So I'm going to take my 1.15 moles of chlorine, and I'm going to put moles on bottom, and then from the periodic table, chlorine's 35.5, and if we have two of them, molar mass is 71. So real quick mole conversion there, 1.15 times 71, and to 3 sig figs, that is 81.7 grams of chlorine. So we do that all the time. We can take the moles, we can bring it out, we can turn the moles into mass, we can turn the moles into a molar mass, we can turn the moles to mass and then a density if we want to. There's lots of things that we can do with this. All right, let's keep going here. I have a few more things I want to show you real quick. Number 4, what is the volume of a balloon if it contains 3.2 moles of helium at a temperature of 20 Celsius? Let's go ahead and add that 273 here. And so that's 293 Kelvin. And standard pressure. All right, so a lot of times we're being told to use standard temperature or pressure. Standard pressure is always atmospheric. Now, it doesn't have to be 1 atmosphere. That's not what I said. I said it's atmospheric pressure. So the number depends on the unit. If I choose to use atmosphere, yeah, then standard pressure is 1. But if I use PSI, for example, the number's not 1. Standard pressure in PSI is 14.7. It's 760 in torr. So you need to specify the unit. But standard pressure, I choose to use my 1 atmosphere. And so that means when I choose my R, I get to pick my favorite one, liter atmospheres over mole K. All right, so let's do this. We got PV equals nRT. I'm going to solve for volume. So if I want volume by itself, it'll be nRT over P. All right, let's plug in here. We got 3.2 moles. We got 0.0821. I'm going to leave the units off here to save a little time. Our temperature is 293 Kelvin. And just that 1 atmosphere, which is basically pointless. We're not doing any algebra with that. So all we have to do really is simplify the numerator. 3.2 times 0.0821 and then times 293. All right, so I'm going to take that, round to 2 sig figs, 77 liters. All right, I'm not taking a lot of time to check my work, so hopefully I didn't use my big fingers and hit the wrong buttons on the calculator, but we're running through it pretty fast here. All right, so we're going to go, got 2 more problems I want to go through. So on the back of this one, again, you should get this handout. It's got the answers at the bottom of each page for just some individual practice at your own leisure. Number 7 here has something I want to go over with you. It's using the ideal gas law to find the molecular mass or the molar mass. You're like, well, that's not in PivNert. It's not. It's not in PivNert. But moles is. And if we remember a very basic definition here, M, and let's actually try to write it in the proper form, which is like a cursive capital M. The units of that are grams per mole. Well, that unit is basically just the formula. So it's mass, little m, over moles, which is N. So I'll rewrite that, M over little n. So if we remember that little relationship, again, just from the units, then we can take the ideal gas law, grab moles out of it if we need to, and we'll come back and use that equation. All right, so let's get to the PivNert part of this. A 23.6 gram sample, well, that's not helpful for PivNert, so I'm going to move on past that, occupies a volume, so there's my V, at standard temperature. We just talked about standard temperature, or standard pressure. Standard temperature for gases is 0 degrees Celsius. That's just what it is for gases. And so, of course, if we convert that to Kelvin, it's 273. So anytime you see standard temperature, 273 for gases. All right, I think I have, oh, it said and pressure. I knew I was missing something here. So standard pressure, we just talked about 1 atmosphere. So we're going to use that. So we're going to solve for N this time. So PivNert, I want to grab moles and pull it out of there. So moles is PV over RT. We did that in the first problem. So let's plug in here. 1 atmosphere is my standard pressure. The volume is 12. And then I want to use my 0.0821 and then 273. All right, so nothing crazy here. Let's take real quickly, let's take our calculator and let's solve this. So 1 times 12 is 12, divided by 0.0821, and then divided by 273. And so N is I'll just go ahead and keep 3 sig figs for now because we're going to move over here. All right, so that's not the final answer. That's just a weigh station on the way. PivNert helps me get moles. But to get the molar mass of this gas, I'm going to go back to this definition. We know molar mass is mass over moles. So we have from the problem 23.6 grams. And we just calculated that means there are 5.536 moles. So just solving that one real quick, this gas is 44 grams per mole. And it could be CO2, it could be propane, but those are a couple of gases that have a molar mass of 44. So the moral of this story is use PivNert for what you can get out of it, P, V, N, and T. If you need something else, take something like N out and apply it to a different equation that you learned a long time ago. All right, I have one last problem that I want to work. For the GT classes, for sure, you're going to do this. If you're not in GT, your teacher may not have you doing density, but I think it's fun to go over. So depending on what your teacher wants, you can stop the video now. If you're in GT or in my classes, let's do this one more problem. All right, so we just learned that one tool that we can use with the ideal gas law is molar mass. So we've got M over N. Another tool that we have is density. We know that density is mass over volume. Now, some problems we can just pull mass out, or pull moles out, convert it into mass, and then take the volume and find density. For this example, I'm afraid we can't do that because the problem doesn't give us any volume. So we've got to use PivNert. So let me derive this one for you real quick. We got PivNert. So what I'm going to do is I'm going to divide both sides by V, like that. Now that's not density, that's moles over liters, which is actually molarity, something we'll get to soon. So I'm on the way, but if I look over here, I know that I can get mass, which is what I want. I want grams over liters, not moles. I can get mass if I just had a molar mass and multiplied it by my N. So what I'm going to do is I'm going to rewrite that, and I'm going to put N times the molar mass over V times RT, and then making sure I follow my algebra rules. What I do to one side, I have to do to the other. And folks, that right there is density. Pressure times the molar mass of the gas equals the density of the gas times RT. So for this problem, if I want to solve for density, it's just going to be density equals pressure times molar mass over RT. Let's see what we got here. Density is, let's see, pressure 650 torr. This is SF4, so we actually need to go to the periodic table and find the molar mass. So sulfur is 32.1 and then fluorine is 19. So we got to add that up real quick. 4 times 19. So that's 108.1, oh boy, 108.1 grams per mole. All right, so that goes here, 108.1 grams per mole. All right, now, once again, I've gone to a different unit for pressure, so my R is going to change. I need to do another pressure conversion. So I'm going to go back to 0.0821. That's in atmospheres. I want to convert it to torr. So I need to multiply it times 760. So that is 62.4 liter torr over mole K. And then the temperature here, 100 Celsius. So we know that's going to be 373. All right, looking at my units, torr cancels, Kelvin cancels, moles on bottom of the top and moles on bottom of the bottom also cancel. So that leaves me with grams over liters. Folks, that's a density unit, mass over volume. So let's simplify. 650 times 108.1. Let's divide that by 62.4 and finally by 373. And that density comes out to be 3.0 grams per liter. And that's it. Alright, so you got some practice. Probably nowhere near as complicated as that, but I want to show it to you. You can do it. Those are some of the tools that we would need. If you have any questions, make sure you ask.